Hi there. Thanks for joining us on another episode of Space Nuts. This is a Q&A edition. This is where we answer audience questions. Well, we read them out or we listen to them and we nod and then we go home. Today, we're going to be discussing white dwarf stars, an interesting question, a double-barreled question, in fact. We've got one about the different size of black holes. Gosh, a question about black holes. How odd. The effect of being in orbit has come up. And Casey wants to know about some of the oddities that exist in the cosmos. We'll cover all of that in this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And Fred brought with him today his brain the size of a planet to answer all your questions. Professor Fred, what's an astronomer at large? Hello, Fred.
Hello, Andrew. Fancy seeing you here.
It's unusual, isn't it, really?
Yes, well, yeah.
We've got a fair bit to get through, so we might just get straight into it. As they say in Britain, we'll muck in.
I think you'll find it's muck in.
Muck in. Muck in. I've got to get the accent right. Yes, of course. All right. Our first question comes from Bloomington, Indiana. 2 questions, if I may, about white dwarf stars. After a very long period of initial cooling, white dwarf stars undergo crystallization before eventually transforming into theoretical black dwarf objects. So the questions are, what is the process of crystallization and how might crystallization slow the further cooling of a white dwarf for such an incredibly long time? Thank you very much for your terrific podcast. Keep smiling in the land down under. That comes from Mark. Thank you, Mark. Lovely to hear from you. We don't talk all that often about white dwarfs, although we have had them pop up a couple of times lately. But yeah, you might want to tackle that process of crystallization first. What is that?
So you need to sort of think about what a white dwarf is before you get to the crystallization.
I suppose so, yeah. Is that what our sun's going to turn into?
Yeah, it is. So
A couple of weeks' time, I think.
it was day after tomorrow, wasn't it? I can't remember.
Yeah.
Anyway,
it's the billionth of a year after tomorrow.
Yes, it's about. So it will be in the region of 5 billion years that
that's okay then.
have to put up with that. So as well, let's take the sun as an example. So the outer. So what basically happens at the moment? We've got this reaction taking place that converts hydrogen into helium and produces a few other things as well. There are other reactions going on, many of which produce carbon, and so carbon sort of builds up in the core of the sun over time, and in particular as it gets nearer the end of its life, it becomes quite carbon rich, the nucleus. So when it sheds its outer atmosphere and turns into what we call a planetary nebula, nothing to do with planets, it's just that the early astronomers thought they looked like planets, but they're actually clouds of gas. Yeah. It's William Herschel who called them planetary nebulae. He called a lot of things their names that we still use. Very eminent astronomer. Anyway, you get a planetary nebula, but the core of the star that's left behind basically collapses under its own gravity because it doesn't have the radiation any longer to support a swollen star, if I can put it that way. Yep. The radiation's gone. So it's incredibly hot, which is why it's a white dwarf. It's because the radiation pushes it into a very extreme white part of the spectrum, a bit like a lot of the headlights on cars these days with their LED, ultra white LEDs. It's that sort of thing, but for different processes. It's very hot. That's why it radiates the whiteness. But it basically is an object with it's in a state of what's called electron degeneracy. And that means that the electrons are the only thing stopping it collapsing into something more dense like a black hole. So it's this electron pressure that sort of stops a further collapse. And essentially, you've got matter does very, very funny things under those circumstances because it's under extreme compression. And so you've got basically a oxygen-rich carbon core, which in the initial stages, as Mark says, after a very long period of initial cooling, that's what he says, in those initial stages, it's liquid. It's a liquid core, a liquid of carbon and oxygen. And it's very hard for us to imagine that. Now, as that cools, it's when the crystallization takes place. It becomes a lattice of, rather than a slushy liquid of these atoms, they form a lattice structure, which we call a crystal. And that, Mark asks, what's the process of crystallization? It's the cooling of the liquid core further. So under the extreme pressure, you get basically diamond forming. That's what it is. And so that crystallization, it means that the core is diamond related. So that's the sort of end product. So that process of diamond formation actually releases heat, what we call latent heat. It releases heat, and so it slows down the star's cooling, and apparently it slows it down by roughly 1 billion years. Wow. And so the suggestion, there's a comment here that I'm looking at that says Gaia data. That's the measurement of the positions of billions of stars and their colours. Recent Gaia data suggests this is a common 10 million year long high density phase. But when you've basically, I'm not quite sure why there's a conflict of numbers there, which I'm struggling to understand. But if you've got the star cooling delayed by 1 billion years, and then the cooling phase keeps on going, you've got then many tens of billions of years before it becomes a cold and dead object, which we call a black dwarf. I don't think there are any black dwarfs yet because the universe isn't old enough for them to have been created.
So they're theoretical, but they're, I suppose, in terms of theoretical, they're probable.
Yes, that's right. That's about right.
Okay.
Yeah, the diamond stars. I mean, it's a nice concept, isn't it?
Yeah. Gee, it's such time frames that you just can't contemplate. It just makes us seem so tiny and small and insignificant, doesn't it?
Yes, although we're important to each other.
Yeah, that's true. I was just doing a bit of research while you were talking. Apparently, they think 97% of stars in the Milky Way will become white dwarfs.
Yeah, that's right. They're the ones that go supernova are the rarities.
That's good, though. I mean, imagine if 97% of the stars in the Milky Way became black holes. We'd all be in trouble.
Yeah,
could be messy.
That's right. Yes, we would. It would be a much more inhospitable universe. If that
Indeed.
Was the case.
Thank you, Mark. Hopefully we adequately answered your question. Great to hear from you. We've got an audio question now. This one comes from Steve.
Hi guys, love your podcast. Keeps me awake a little later every evening listening. Steve here from Tin Can Bay in Queensland. Very dark sky place, actually. And my question is to do with different sized black holes and gravitational gradient. Not that I know much about this. I was wondering if you fell into a smaller black hole, I believe there's the spaghettification effect, where the gravity at one end of your body to the other would tear you apart. That if you free fell into a super large black hole, wouldn't the gravitational gradient be more even out across the plane and you will just free fall into it. Sure, Fred can explain that and make more sense of it.
Thank you, Steve. Tin Can Bay, what a beautifully named place. I love it.
Have you ever been, Andrew?
I haven't been there, no, I haven't.
I haven't either.
Yeah. Sounds like it's a great place to visit, especially at night if it's a dark sky area.
Yeah,
fantastic.
dark sky, yeah, check it out.
So we're talking about different sized black holes, and if you fell into them, well, we all know what would probably happen, but what if it's super large? Is its gravitational gradient spread evenly, and does that mean you could fall into it without too much trouble?
I think so. If you think about the gravitational well, the shape of this this sort of vortex that is the black hole in gravity, yes, for a bigger black hole, it will be less steep. It will basically extend over a much wider area than for a small black hole, and will start off less steep because it's a gentler slope. Which means, and what that's telling you is the event horizon is bigger for a larger black hole, a larger mass black hole. But the end product is pretty well always the same. Maybe your spaghettification will be a bit gentler, but you're always going to end up in a very, very steep gravity gradient. And yes, I think... Steve's thinking, I think, is right. The way that gradient changes is what tells you how quickly you're going to be spaghettified, and it changes more slowly for a larger mass black hole than for a smaller black hole. But you're still going to wind up in deep trouble. You're still going to get spaghettified in the end.
Yeah, I suppose depending on the size and gravity effect of the black hole, it could be spaghettified or linguinified. It could be variables like that.
It could be, yes, that's right. Yes, they could. Yeah.
Or butterfly pastified. That would be really different.
Yeah.
Very unusual. But I think in the movie Interstellar, they broke the laws of physics when they actually did successfully go through a black hole at one point in that film.
Yeah, I think they did.
But I think they described it as it was a supermassive black hole, but it was very, very well tempered. Something to that effect. But yes, because what they were looking for was only available to them in terms of research on the inside of a black hole. And so they had to go in there and find what they needed to save the world.
Yeah. Yes, that's right.
Great film, though. One of my favourites. Thank you, Steve. Hopefully we answered your question today on Space Nuts. And you're listening to a Q&A edition with Andrew Dunkley and Professor Fred Watson.
0G, and I feel fine.
Space Nuts.
Okay, next question, Fred. Over the years, Fred has explained how astronauts orbiting the Earth are affected by gravity about the same as us because they are, in effect, continually falling. When they leave orbit and head into space, how far do they need to travel before they no longer feel the effects of gravity? Also, when they orbit the Moon, is it the same as orbiting the Earth? That one comes from Wayne. Hi, Wayne. Thanks for the question.
Yes. So how far do you need to go?
I had a question, but it dropped out of my head. But I suppose that the first point we look at, if you're orbiting Earth, you're continually falling.
Yeah.
But you're still feeling weightlessness, aren't you?
Yes. So that's how it works. You're being pulled towards the centre of the Earth by gravity, and you're feeling much the same gravity as we do on the surface. But what's stopping you from falling is your forward motion. You're always moving in an orbit that means that you never actually reach the centre of the Earth, which is just as well because it's not a nice place.
No, not really.
But okay, so then you fire your rockets, you do translunar injection or whatever that is, wherever you're going. If you're going to the Moon, it's a translunar injection. That's what they call it, which takes you from the orbit that you're in, a circular orbit around the Earth, and puts you into a different orbit, which will carry you out towards the Moon. And if you don't do anything, as happened with Artemis 2, there were a couple of minor course corrections, but basically that will bring you back to Earth because you're still in an orbit. Even though it's a very long, thin one, it was a figure of 8 one in the case of Artemis 2. But you're still in orbit. You're still being pulled towards the Earth. The Earth's gravity is reducing as you go further out, but you're still feeling it. And okay, if you go out to Saturn, you're still feeling the Earth's gravity. You're actually, there comes a time which is when you expand your voyage beyond the Earth-Moon system. There comes a time when you're feeling the sun's gravity more, and so you're kind of technically in orbit around the sun, and that's what happens with interplanetary probes. You go to Saturn, you're in an orbit, but you're still being pulled back towards the sun. And if you don't do anything when you get to Saturn, like fire your braking rockets to slow you down to put you in orbit around Saturn, if you don't do anything, you'll wind up going back to the sun. You'll end up coming back.
Is that what's happening with comets and asteroids?
Yeah, they're just feeling the pull of... So comets in particular, out there in the Oort cloud, they get a little bit of a nudge. That means that their velocity is not enough to keep them from falling in towards the sun. And so they do. Yeah. And it takes them a long time to get in towards the sun, hundreds of thousands of years. But they still do it. They're still in orbit.
Okay. So how far would you have to go outside the solar system to not feel that effect?
You're
always going to feel something somewhere.
Yeah. Gravity's not something that disappears. It actually falls away and effectively becomes zero at very big distances, but it's still there, as witnessed by the Oort clouds a light year away or something like that. What eventually happens in interstellar space is you still feel the pull of stars around you, including the sun, but you're also under the influence of the galaxy itself. So our sun, for example, is in orbit around the galactic center. It's falling towards the galactic center, but its velocity of 200 kilometers per second. It's actually about nearer to 250 kilometers per second around the center of the galaxy. That's what's stopping it falling in towards the galactic center. Goes around in about 200 million years.
It's weird.
Yeah, it is weird. It's very weird.
I mean, we're talking about that next with oddities in space, but that's one of them. I mean, we've got this situation where these things have been doing this for billions of years, and that's not going to stop in a hurry. And even when our solar system ultimately has the sun go, boom, it's still going to be happening like that. Is it not?
Yes. Well, I mean, the sun will swell to possibly engulf the inner planets, but the centre of its gravity is still where it is now, effectively. So, yes.
What about maybe, getting yourself into a Lagrange point?
Yeah. So that's where those points are where gravity and often centrifugal force balance out. So you've got this stable point. They're not that stable, actually. You can tip one way or the other. It's more like a saddle in the gravitational pull, but they're more stable. And I was actually going to mention that that leads then to this idea of the interplanetary superhighway. The planets and their Lagrange points are kind of interlinked by these low energy pathways through the solar system. So if you push an object into one of these low energy pathways, they are feeling the gravity of not just the sun and the earth, but the moon and other planets as well. But they can wander their way along one of these pathways till they get to the other Lagrange point. And that's something that's been looked at for slow speed interplanetary travel, maybe for supply ships or something like that, but you're going to take decades to get to wherever you want to go.
Yeah, and by then your iPhone's probably defunct. You know, the technology would be too old.
Yeah. Yeah. Yeah.
Yeah. So if you get far enough away from the pull of the Earth and the Moon, the sun's going to grab you.
You feel other things as well. Yeah. Jupiter's another.
Oh yeah. Well,
big force. Yeah.
It does not like being ignored.
No, it doesn't. That's right.
No. In
Especially
fact, that's another factor in our solar system, that Jupiter, because of its size and gravitational effect, is a good barrier for Earth when it comes to big rocks heading in this direction.
That's right. That's been postulated as one of the reasons why the Earth has evolved life, because it's protected to some extent, particularly by comets, from comets, by Jupiter, which turns a lot of comets from having fallen in from the Oort cloud. They get grabbed by Jupiter's gravity and become what we call short period comets. But I've read papers that say the opposite is true. Jupiter's effect is not as protective as we'd like it to be, and maybe some of Jupiter's malevolence is when it redirects comets into short period orbits and we run into them.
Ooh, yeah.
Yeah.
Not nice. Not nice at all. So basically, it doesn't matter where you go, you're going to be affected by some sort of gravity.
That's right. Yes, you will. Even if you're deep in interstellar space, you'll still be feeling the effect of the gravity as a whole.
So does that mean weightlessness is a myth in real terms?
Yes, in a sense it is. It's weightlessness weight needs gravity, and if you are experiencing forces that balance that force of gravity, then you're weightless, and that's what happens when you're in orbit.
There you go. All right. Good question. Thanks, Wayne. Lovely to hear from you. Our final question in this episode comes from Casey.
Hi guys, this is Casey from Colorado. There's a lot of weird stuff in space, and I was wondering what some of your favorite oddities are. Thanks for the podcast, and shout out to Hugh for fixing the audio submissions. Bye.
Thank you, Casey. Oh, Hugh did some work. My goodness. Only took a couple of months. No, thanks, Casey. Oddities in space. I love this question because there are many. If you go through an official list, of course, number one would be dark matter. Number two would be dark energy. Those are obvious. Have you had to think about this one, Fred? What have you come up with?
Well, we've just been talking about something that's really odd and counterintuitive, a diamond star.
Yeah.
A metal asteroid, that will be an oddity. We think Psyche is a metal asteroid. We'll find out when the Psyche spacecraft reaches Psyche. I think in 2031 or thereabouts. I think it's got a way to go yet. Maybe not that far. Anyway, I'm sure it's going to happen. But I think some of the coincidences are oddities, and the one that always blows my mind is the coincidence of the sun and the moon looking to be the same size in the sky. That's a complete random thing with no physical mechanism that has caused that. And you've got these two objects which are the most prominent objects in our skies, and they appear to be exactly the same size.
And it's just a coincidental proximity thing, isn't it?
Very weird.
Yeah. Actually, I've got one that involves the moon I just found, and despite the fact that we look at it in the night sky and it's round, they say it's lemon shaped. Is that true?
It's got a slight deviation, yes, that's right. That there's a bulge because it's always because it always faces the same side to the Earth. I think it's slightly elongated in that direction.
Okay.
I think that's the case, but in from the direction we see it, because that lemon shape is towards us, what we see is an object that is almost perfectly circular, the moon. Very, 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 very perfectly circular.
And while we're talking about that, because you just popped into my head while you were talking, the sun, in terms of being spherical, is almost the perfect circle, isn't it?
It is. It differs from being spherical by something like 10 kilometres and it's 1.4 million kilometres in diameter. That's right. And actually that raises another oddity in my mind, which we've talked about many times, the mountains on neutron stars.
Oh, yes.
Which are a few millimetres high.
Yeah. That's just crazy, isn't it? Yeah. I mean, if you do Google searches for these things, there's millions of them. But, if we stick to our solar system for a moment, a day on Mercury is twice as long as a year.
Yes, that's right.
Is that because of its, what do you call it?
Tidal locking.
Yes, tidal locking to the sun.
It's not quite tidally locked, but there's a relationship between the rotation and the revolution period, which is what you've said. Yeah. Very weird. Yeah, some of the planets have very weird things. I mean, Uranus on its side, that's an oddity. That's very strange, but we think that's caused by a collision in the early solar system.
Yeah. All the planets could fit between Earth and the Moon.
Yes, that's right.
I mean, that just blows my mind. Go ahead. No, that would make for some very interesting nights of observation, I imagine.
Yeah, and it's an issue. It's quite interesting because the moon's orbit around the Earth is not circular, so sometimes it's nearer than at others. Perigee is when it's at its closest, apogee is when it's at its furthest. The planets, the 7 planets, because the Earth's not part of it, they will only fit between the Earth and the Moon when the Moon is near apogee. If it's near perigee, you can't squeeze them in and it becomes a bit ugly, really.
Yeah, I imagine so, yeah. I like this one. A teaspoon of neutron star weighs the same as the human population. I don't know how they figured that out.
Yes, that's right.
That's true. But they're very heavy.
The one I like, the numerical one that I like is, and again, it's completely bizarre. It's got no reason for it. But the number of astronomical units, and an astronomical unit's the distance from the sun to the Earth, 150 million kilometres. The number of astronomical units in a light year is almost exactly the same as the number of inches in a mile. It's very, very weird. 63,000 is the number. So there's a few digits that don't fit, but yeah.
That's incredible. And then there's these ones that sound weird, but are so logical when you explain it, that there are stars in the universe that we will never see.
Yeah, yes, because the light will never reach us. That's right.
And that's probably why we'll never, ever find alien life, because they're too far away.
Maybe. Maybe. Who knows? The SETI people aren't giving up.
No, they're not. Now, I did say that a day on Mercury is twice as long as a year, but on Venus, I think it's a similar story, isn't it? A day on Venus is longer than a year.
Very long. Yeah, I can't remember the details, but Venus basically rotates the wrong way around. So its north pole is facing downwards, and that's what gives you the funny rotation. You define the north and south poles as being the direction or the point on a planet where, if you're looking at it from above, it's rotating anti-clockwise, because virtually everything in the solar system is rotating and revolving anti-clockwise as seen from above the North Pole.
Weird. Oh, you like this one, Casey. Neptune has only completed one orbit since it was discovered. Very quirky. And look, there must be billions of these, like, the weirdness of rogue planets, or the sun losing 1 billion kilos per second. Now,
that's right, yes.
If you found out the secret to that, somebody could make billions of dollars on Earth, I reckon.
Needs quite high temperatures to do that.
Yeah. And the list goes on. You got any more?
Well, even black holes are things are so weird, and the fact that we can... Actually, here's another statistic that's mind-blowing. It's the LIGO interferometer, which measures gravitational waves, the accuracy that we position it the mirror or know the mirrors to is something like 1,000th of the diameter of a proton. It's just incredible. But that's technology rather than space oddities, really. That's technology.
Yeah.
That blows my mind too.
And another one that's not talked about much, but our days are getting longer. I think there was an official report not so long ago about the new length of a day on Earth, but they are getting longer because our rotation's slowing. Is that what it is?
Yeah. It actually speeds up occasionally as well due to probably the movement of ice and things of that sort.
Yeah.
But the overall trend is definitely a slowing of the rotation.
Yeah, there are so many of them, Casey. And if anybody comes across one they'd like to ask us about, please send it in. But thanks, Casey. That was a lot of fun. And that brings us to the end of the show, Fred.
Yes, another show in the bag. And
yeah. Or in the can, as you know, that's the shop talk way of saying it.
Shop talk, yes.
Yeah, in the can.
In the can. And hopefully there'll be many more, Andrew.
That would be lovely. We'll catch you on the next one in a few days' time. Fred, thank you.
Sounds like it. Thanks a lot. Take care.
Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio, who couldn't be with us today due to some kind of oddity, a space oddity. And don't forget to visit us online at our website or on social media and send us your questions via the Ask Me Anything link at the top of our webpage in audio form or as a text. And don't forget to tell us who you are and where you're from. Always lovely to hear from you wherever you are in the world. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.